Thank you for coming. I'll tell you about a few new results on understanding neural networks. So I'm interested in understanding learning. What properties of the physical world allow us to learn well and allow us to learn efficiently. So, in a sense, if you are any good at saying what good learning means, then this kind of theory or this kind of mathematics should also translate to understanding why biological systems learn well. They clearly learn much better than artificial systems. And so this is the eventual goal. I won't talk about it. This talk is focused on understanding artificial neural networks. If you're interested in this question, I would contend that there is two key big questions that we do not know the answer to. The first one is, why can we train neural networks well? We like networks that can do lots of diverse, that work well on lots of diverse data. And to model all this variability in the data, we need to have a lot of parameters. The tasks that we would like them to do, the labels that we are predicting, are complicated functions of the inputs, and that is why the functions that that the networks parameterize are complicated, in particular non-convex. By all intents and purposes, non-convex optimization problems, which is what training a neural network amounts to, are hard optimization problems. So if you ask friends, they'll tell you that 10-dimensional non-convex optimization is intractable. It doesn't really make any sense that we can train these networks in millions of dimensions, right? This is the kind of questions that I was asking during my PhD, and the rough summary of my work, many other people's work, is that the energy landscape of neural networks is not convex, yes, but is somewhat benign. So it looks a little bit like the Grand Canyon. No matter where you are standing, there is the river below you. Doesn't matter which part of the river you fall in, it's the same river. There is crevices and stuff where you can get stuck, but we have figured out tricks to escape those things. So it's not trivial, but it's not intractably hard either. Okay. The second question is, in high school, everyone told you that if you have 10 data points, you shouldn't be fitting a polynomial of degree 15 to these 10 data points, because it can overfit and it can be very wiggly in parts of the domain where you do not have enough data. In deep learning, we love doing this. We don't even seem to get hurt by doing this. So something must be easy about the problem that we are trying to solve. Otherwise, this wouldn't work. So this is the kind of questions that I hope to shed light on in this talk. But maybe before we go to the answers, it behooves us to ask, why do we care? If you ask the practitioners, they are not exactly waiting for answers to these questions. They are doing fine, way better than fine, without knowing anything about this. I'll give you two answers, two of my answers. And the first one is simply pride. Okay? We have been taught some stuff in textbooks. These neural networks clearly seem to go against those things, at least at the face of it. So are the textbooks wrong? Should we just burn them? Or maybe we did not understand the textbooks as well as we think. Okay? The second thing is perhaps a bit more important. I believe that the success of deep learning is telling us new things about the nature of data. It's a little bit like building a new microscope. Over the last 10 years, 30 years, depending on how you count, we were trying very hard to build a good microscope. Now we have a great one. But the reason we were doing all this was to look at what is underneath the microscope. And so I would like to understand what natural data looks like. And the fact that the networks are working well is just the first step of that process. Okay? Okay. So over the years, I'm not the only person asking these kinds of questions. Many other people have asked these questions before. And in our attempt to explain the efficacy of these networks, we have attributed a lot of mystery and peculiarities to them. And I'll give you two examples from my research. There's many others in other papers. Here's one. Okay, so a few years ago, we noticed that after training, typical neural networks end up in regions that are rather wide in the energy landscape. Okay, so if you calculate the Hessian, which is the curvature of the loss a quantity that tells you how quickly the loss changes locally, you will notice that the Hessian has a lot of near zero eigenvalues. And that tells you that about 95, 96% of the eigenvalues are essentially zero. That tells you the loss function, no matter which direction you look at, is quite flat. There's also some positive ones, there's also some negative ones. But typically, at the end of training, for most networks, for most algorithms, you reach regions of this kind. If you reach regions that are not this wide, then you do not seem to get good test errors. So there is a utility, or there is a merit to reaching these kinds of regions. But a lot of calculations in statistical physics will tell you that wide regions are rare in the energy landscape. These are what are called large deviations phenomena under certain models. And so you should think of it as a little bit like you're in this gigantic room. There are many solutions to the training set in this room. There is one particular kind of solution, which is this wide region. It doesn't make sense that you're finding this tiny part, which is very rare, with local descent algorithms. Okay? And you do. So every time you train a network, you'll get a Hessian that looks like this. We didn't know why it happens like this, why it is so. So we chose a slightly simpler problem. We said, look, the energy landscape has both wide regions and not wide regions. Let us try to modify the loss. So if f of w is a training loss, g sub gamma is a Gaussian kernel of bandwidth gamma that smooths the loss. And this smoothing basically destroys all the regions that are not wide. It keeps the regions that are wider than gamma. And then it makes them easier to find. These algorithms also work very well, so they are about 2 to 4 times faster than SGD. Still some of the fastest methods I know to train neural networks. So you can exploit this peculiarity. But the point is that you are ending up in regions like this, even if they are somewhat rare. Okay? Here's a second example. We noticed that the noise in SGD, which you can characterize as the covariance matrix of the stochastic gradients, how different is the gradient of a one mini batch from the full gradient on the entire data set. This is a matrix whose size is number of weights times number of weights. It is quite close to the Fisher information matrix, which defines the curvature of the output of a model, roughly speaking. Okay? And we noticed that the noise is very pathological in most networks and most data sets. Out of these millions of dimensions in the weight space, you have noise in less than 0.5% or so dimensions. All the other dimensions are basically doing gradient descent dynamics. And now when a physicist looks at this, they will call it a non-equilibrium stochastic process. This stochastic process doesn't have detailed balance because taking a trajectory that goes in one direction is not the same probability as the trajectory that comes exactly in the opposite direction within the same 2 points. Okay? And such things are somewhat exotic. Markov chains with broken detailed balance. Even in biology, you need some constant amount of energy that is being added into the system for the entropy rate to not be zero. And you can get lots of exotic phenomena. For instance, we showed that the most likely locations that you can find SGD at the end of training are not even the critical points of the training loss. Okay? So before this, we were wondering whether or not you find global minima in non-convex data landscape. This result says that you don't even find local minima, or you can happily converge to regions around local minima. Okay, so it seems a little bit spooky. You will also be able to show that the networks, the weights of the network can evolve in subspaces arbitrarily. They don't have to converge, they don't have to stop, so long as the gradient of some function phi is zero. It's not very important at this point what this function is, but this is peculiarity number 2. You have a very pathological noise in the way we are computing gradients, and that gives us pretty exotic phenomena even by the standards of physical systems. It's an artificial system. Okay? And there are many other examples. So what I want to convince you of is over the years, there are many such versions. So for instance, some people might say that if you want to understand neural networks, we should really understand what overparameterization is. Because they seem to be, they're distinct from the other machine learning models we know in the fact that they have so many parameters. And I don't know, if you think a little bit like a first-year undergraduate student, I have many parameters. I do not have enough information to constrain all these parameters. So why the heck should they matter, the ones that I do not constrain? Over-parameterization cannot be the only game in town to explaining why these networks work, because I'm not even constraining all the other parameters. Okay? If you ask some other people, they'll say, oh, inductive bias is the reason why these networks are special. Well, inductive bias was the reason why convolutional networks were so successful in 2014, 2013. Transformers are also exactly as successful, if not better. Okay? So it cannot be that inductive bias is, again, the only theory that explains why the networks work. And you can kind of go around the room and then lay blame to gaps in arguments of many different attempts to understand this. What I want to convince you in this talk is that we are missing the elephant in the room. The data that we train these networks on is kind of special. And that is really the secret of all these peculiarities, or that is really the reason for all these mysterious properties. And if you were to understand the data a bit better, we can explain them. Okay? So first, I'll tell you a result that we presented at ICML last year. It's a paper called "Does the Data Induce Capacity Control in Deep Learning?" Okay, and focus on the blue line for a second. The blue line are the eigenvalues of principal component analysis of CIFAR10 images. CIFAR10 has 10 classes, 32 cross 32 pixels, RGB, so 3 channels. So it's 3072 eigenvalues. And what you notice immediately is that the ratio of the largest eigenvalue, which I have normalized to 1 here, and the smallest one is 10 raised to 8. This is a gigantically low-dimensional data set. So if you think of a point cloud of the images, this is an ellipse that subsumes this point cloud, and the longest axis of the ellipse is 10 to the 8 times longer than the smallest axis. In computer vision, we've always believed that inputs, typical images, lie on low-dimensional manifolds. It is not exactly low-dimensional because there is also these small eigenvalues, but it is effectively low-dimensional. About 100, 150 dimensions are taking most of the bulk of the variance of this point cloud. Okay, if you think a little bit about this, you can also convince yourself why this is so. This is a picture from Plato's theory of forms. So you can imagine that along the long axis of the ellipse, on one side lie all the pure cats, on the other side lie all the pure dogs. And then the other axis, the longitudinal directions, consist of aberrations. So blue sky, which doesn't change very much, would be along the small eigenvector. Blue dog, there is not very many of them in the world, would also lie along the small eigenvectors. Okay? We call such a spectrum sloppy. This is just a name, and here is why we named it so. We showed that if the input data looks like this, if the input data decays very sharply at the beginning and then is linear on a log scale, then essentially any quantity that you calculate inside the network, be it the Hessian, which is the curvature of the loss, we just saw it, the Fisher information matrix, which is the curvature of the output, we also talked about it, correlations of activations, correlations of Jacobians of different logits, basically anything that you can calculate also has a spectrum that looks like this. It decays very quickly in the beginning and then slopes down with some rate. Okay? The reason why we call this sloppy is as follows. So think of an eigenvector here with a very small eigenvalue. It is corresponding to a direction in the weight space where I'm allowed to perturb the weights by 7, 8 orders of magnitude before I see any appreciable change in the output of the function. Okay? So this is gigantical, really stark, big redundancy in how the network uses all its weights. This is a wide residual network with all bells and whistles, about 3 million weights. But the network is using only about 150 or 200 or so parameters to actually make the predictions. All the others are decorations of the accuracy. Your 95% accuracy is coming from the head of the spectrum, and then if you want the remaining 5, sure, you have to dig all the way deep into the tail. The tail is also very long, and it has a very bad aspect ratio. Okay? The reason this is important is because you can imagine that if noise were to come and change this part of the spectrum, you would see zero deterioration. The output of the model is insensitive to changes that happen in this subspace, and so you cannot overfit on such data sets. Okay? Nothing can, not neural networks, nothing can. Okay? So we have also noticed that the labels are highly correlated with the head of the spectrum, and that has some post hoc explanation in the sense that you have images of cats, and you give them label cat based on the salient features. You don't give labels based on non-salient features, so they got to be correlated with the salient aspects of the input. If data looks like this, if the task looks like this, then nothing can overfit. Okay? If the orange line or the blue line was genuinely low dimensional, it was dropping like this, then we would all be solving easy problems and we wouldn't be very proud of ourselves. If the blue line was flat like this, then you would see the curse of dimensionality, and then you couldn't solve those problems. Okay? So in a sense, this decay is the right level at which we are allowed to solve these problems in a computationally reasonable way, and yet solve interesting enough problems that we care about. Okay? Just a quick picture of the mathematics. We would really like to show that sloppy inputs, so the blue line being shaped in this peculiar way, lead to sloppy Fisher information or sloppy Hessian. We can't quite show this entire sentence as is, so that is why I put a little tilde here. We can show it in parts. So we can show that the trace of the Fisher and the trace of the Hessian is upper bounded by the trace of the input correlation matrix. The input correlation matrix is exactly whose eigenvalues I was plotting, the blue line. And then there is a bunch of terms that depend on the weights. Now, this is a rather simple inequality to show. The way to interpret this is as follows. So imagine that I have a network where I force the weights to lie within some L2 ball, and so I can uniformly bound this entire term. And I start taking the I start increasing the size of the network. It doesn't have to go to infinity, just has to grow big. This entire right-hand side is a constant. The left-hand side grows more and more terms. So at least that tells you that the eigenvalues of the Fisher or the Hessian have to decay. Doesn't tell us that they have to decay exponentially, but at least they got to decay as 1 over k or so. Right? That's just about a trace. If you look at the blocks of the Fisher information matrix, the blocks of the Fisher matrix are the correlations of the Jacobians for weights that correspond to only that particular layer. You don't go across the layers when you calculate the block. We can give a slightly more precise bound on the entire spectrum. So the eigenvalues of the block of the Fisher information matrix are upper bounded by the eigenvalues of the activations, or the correlations of the activations of that particular layer. Again, not a very difficult thing to show, a short calculation, but this tells you that if the activations are sloppy, then the Fisher information matrix also has eigenvalues that decay. So it's very difficult to go directly from the inputs all the way to the Fisher, because you cannot get very general bounds on the activations as you go up the layer. For infinitely wide networks or for kernel machines, all of these things can be done pretty easily. You can show that sloppy inputs gives us sloppy Fishers. Okay? So there is some insight into mathematics. What I want to tell you next about is that all the stuff that we've talked about, sloppy inputs and sloppy Fishers, doesn't seem to be very specific to neural networks. Many models in nature are sloppy. So I've shown you an example of a particular systems biology problem. This is an extracellular regulated kinase, ERK half. This is, you can think of it as a catalyst for the growth of cells, PC12 cells in particular. And people have noticed that, for instance, there is a protein called EGF, epidermal growth factor. If EGF is large, then ERK shows spikes. If ERK shows spikes, then the cells increase in numbers. They all remain the same, their function is the same, but they increase in numbers. If the neural growth factor is large, if this protein has a large concentration, then the cells differentiate in their functionality. Okay? This is just a particular kind of reaction. And those details are not terribly important at this point. For us here, you can think of this entire system as a coupled system of differential equations. The output of this system is the kinase, is the catalyst. The input to this system, or the parameters of this system, are the concentration of proteins that play a role in this, or the kinetic rate constants of all these reactions, whatever you pick. we are allowed to calculate the sensitivity of the output with respect to perturbations of the parameters. And these are, again, the eigenvalues of the Fisher information matrix, or Jacobian, if you want to think about it that way. When a systems biologist sees these kinds of eigenvalues, they're happy, because they'll say, of course we know that the output is insensitive to many, many changes in the parameters, because that way your body can make sure that functions remain intact even if the environment changes a tiny bit, right? So this makes sense in a post hoc way. There is a pretty cool question that I believe we are trying to solve right now is why did this circuit have to become so? And the basic theory or the basic line of attack is when a system wants to become resilient to changes of the environment, then it has to become sloppy to preserve its function. Otherwise, it would be too sensitive to changes in the environment. Okay? So systems in nature are sloppy. Many, many others are systems are sloppy. Doesn't have to be a natural system. So an Ising model is a pretty fake model that physicists use to understand disorder in materials. You can think of it as a bunch of spins. You and your neighbor like to take the same value in the sense that both of you point up if the coupling constant between these spins is positive. If the coupling constant is negative, then the spins are pointing in opposite directions. Now, in statistical physics, people have a pretty sophisticated understanding of why the Fisher information matrix, in this case it would be the sensitivity or the probability distribution of the spins to the coupling constants, has such sloppy eigenvalues. Is because this is classical constructions where there are some macroscopic quantities that emerge because they don't depend in sensitive ways on all the disorder in the system. And that is why for inanimate matter or for these kinds of systems, we know pretty nice way for why the system has to be sloppy. It is more of a matter of asking a different question. If you wanted to understand the magnetization, which is the average value that the spins take, then it is a sloppy model. If you wanted to understand the actual value of the spins, then it is not a sloppy model. So the most important thing to appreciate from all this commentary is that sloppiness is a property of the trained model. But it is also a property of the question that you're answering with the trained model. If you want to know the locations of molecules in this room, then you would have a very complicated model, and it would not show this simplicity. But if you want to identify a cat, then it doesn't depend on all the pixels in the image, and then you're talking about sloppy models. Okay? Let me show you one example, one application. So I'll talk about what I call pack-based bounds. Pack stands for probably approximately correct. Learning theory people will write inequalities of this kind. So they'll say, take a probability distribution Q on the hypothesis space or on the weight space, if you will. Little e of Q is the probability that you make a mistake on a test datum for a hypothesis drawn from random from the distribution Q. Okay? Something smaller than 1. E hat of Q is the probability that you make a mistake on the training datum. Okay? And then they'll say the probability of making a mistake on the test is less than the probability of making a mistake on the training set plus some complexity term. And it's not very important what P is at this point, but the way to interpret these kinds of inequalities is if Q puts its probability mass on many, many different hypotheses, then you need requisitely large amounts of samples to distinguish between all these hypotheses. If Q puts its mass on many of them, then it cannot possibly pick one hypothesis with few samples. Okay? And this is how people will think of them. And in this form, it is about 30 years old, maybe more. What has recently been noticed is that when we plug in numbers into these inequalities, things don't quite work. So a typical neural network will have basically zero training error because you're interpolating the data. And so this term is 0. The test error, let's say it is 5%, so this would be 0.05. But the complexity term is much larger than 1. It will usually be about 100 even for MNIST. And so you don't really need a theory or certainly a theorem to say that the probability of making a mistake is less than 100. It's obvious, right? And so this is why people have been very anxious about this, and they call such bounds vacuous. They're vacuous not because we did anything wrong while deriving this equation, this inequality, but we don't know. It's because neural networks have a large number of parameters. That is why this term is very large. Okay? What we showed in this paper is that we can give an analytical non-vacuous bound on the generalization error of general neural networks simply by an assumption that says that the inputs are sloppy. If the inputs are sloppy, the Hessian is sloppy. If the Hessian is sloppy, then you can get a non-vacuous bound on the generalization error. It's not tight. It's 0.38. Whereas a typical MNIST network will have this kind of a test error, which is called a stochastic test error of, let's say, 2%, 3% or so. And in the paper, you can also develop some numerical techniques to get basically pretty tight inequalities on the generalization error. But the point of the entire argument is that you don't need new theory to understand deep networks. The existing theory works just fine. You just have to apply it in the right way and appreciate the fact that you're not fitting arbitrary data. You're fitting data with very specific patterns, very specific learnable patterns. Okay? You're not fitting a hash function. Yeah.
So in principle, if I choose a better prior, would I be able to make the right-hand side much smaller?
Yeah, that's called transfer learning. Yeah. Cool. So here is one take-home message from this calculation. Let us ask ourselves, there are many, many weights in the network. How many are really constrained? So we can pluck out a quantity which is, roughly speaking, the elbow of this particular eigen spectrum. That looks as follows. The number of eigenvalues of the Hessian that are larger than epsilon is not important. It is a scale of the prior. The denominator is 2 times the number of samples minus 1. Okay? And now this is quite beautiful. So it tells you that if I give you an infinite number of samples, then the network actually uses all its parameters. All the parameters are necessary to make predictions on this infinite amount of data. But if I don't give you enough samples, then because of the shape of the eigenspectrum, you're not using all the degrees of freedom available to you. You do not have enough information to constrain all those degrees of freedom. Typically, in practice, only about 0.5%, not 50%, 0.5% of the number of weights are actually constrained. Okay? So when someone says, I fit a network with 1 million weights, they're really fitting a model with about 5,000 degrees of freedom. And it shouldn't be a surprise at that point that we can get good test error. The networks are secretly small. We just lie about them to everyone. So here is a cartoon of this entire business. If you think of the manifold of functions that are expressed or that are expressed on this data by the network, the learning typically happens in the stiff part of the eigenspectrum. If you take out the Fisher at initialization, the weights predominantly move in the stiff subspace. They don't move in the sloppy subspace for 2 reasons. One is because these are optimization problems that are low dimensional, yes, but they're incredibly badly conditioned. So even if you take a quadratic with an aspect ratio of 10⁶, you're not going to be able to minimize that very easily, right? But it doesn't matter because the sloppy degrees of freedom do not affect your predictions much. You're already getting the 95% accuracy, and the remaining 5 is coming from the sloppy parts. Okay? So you find learning corresponds to you initializing somewhere in the interior of such a manifold and then fitting the long sides of this. And we call such manifolds hyperribbons. They're very long in some directions, and then there are many, many, many directions where the ribbon is very thin. It's just like the ribbon that you use in everyday life. Okay? So over the last year or so, we've been basically making this picture more and more rigorous. And this is the subject of 2 papers. The first one will be presented at ICML in a couple of months, and the second one we just put out an archive last week or so. Here is how I will explain that. So I would like to understand the space of probability distributions that are expressed or parameterized by the network when it learns. Okay? This is an infinite dimensional object. So P of y given x, y is an output, x is an input, w are the weights, is a function of x. I can plug in any x into this that I want, I get one number, right? It's not very easy to understand such an object, 1, because it's a big function, and 2, because the likelihood is a complicated function of the weights. That is really the grief of the entire business. We do a pretty cheap trick to get around this. It's a little bit like someone told you to take a function analysis class, you did not take it, so you take the function, you measure it at a fixed finite number of points, and then now you pretend that you have a vector and forget that you're dealing with a function. Okay? In our case, The points at which you want to measure the likelihood are pretty naturally selected. These are simply the training samples. So if you think of ImageNet, ImageNet has 1 million samples, so n is 1 million. For each of these samples, you are predicting 1,000 numbers, 1,000 probabilities for each of the 1,000 classes. So you have 1 million times 1,000, which is 1 billion dimensional vector. That is a representation of the model that you have learned. Doesn't matter what architecture you have, doesn't matter how you train this model, so long as two networks have this exact same vector, they are the same models, at least as evidenced by the samples in your training data set. You could have other samples where the two functions differ, and you wouldn't know about it in this business. Okay? So here is what we will try to do. In this space, let's say that you have a billion dimensional space. It's not a vector space, but it's a product manifold of spheres, of 1,000 dimensional spheres on which the probabilities lie, and 1 million product of such spheres. On this manifold, 2 points are kind of special. The first one is what we like to call the truth. It is the one-hot probabilities of all the samples, which is the solution of the training set. This is what we want to fit at the end of the day. At the beginning, people like to initialize their networks so that the network predicts 1 over 1,000, 1 over 1,000 for every class, for every image, right? That is what we call ignorance. So the name of the game when you train a network is you begin training at this point called ignorance. You end training at this point called truth. And then you are now doomed to live in this billion dimensions. And the question is how you get there. Okay? This is a legitimate probability distribution, so we can define distances between 2 points. If you have two distributions, PU and PV, we like to use what is called the Bhattacharya distance. The Bhattacharya distance, if you haven't seen it before, it is for the purposes of this calculation, you can just think of symmetric K divergence. The reason to use this is as follows. So in these dimensions, anything that you use to measure distances between points goes to hell pretty quickly. It saturates. So if you take the Hellinger distance in these dimensions, it will always saturate. So you have to use things that are not metrics. The Bhattacharya distance or the symmetric KL divergence is not a metric. It's a distance. It's positive, but not symmetric. The KL is not symmetric, but it doesn't satisfy the triangle inequality. And because of that, you can get confused when you interpret these kinds of calculations because triangle inequality is not valid. But we have figured out ways to work around that. So here is what we are going to do. I'm going to train hundreds of thousands of models in this space and then project them down into lower dimensional spaces to understand how the training process behaves. Conceptually, it's a lot like doing PCA, principal component analysis. We use something called as multidimensional scaling, slightly more old-fashioned, but this is same calculation as PCA, essentially. PCA preserves Euclidean distances between points. MDS preserves your favorite distance, in this case, the Bhattacharya distance between points. Okay. Now, another thing that is pretty cool and technical about this is that typically MDS is very popular in the bioinformatics literature, where they'll use it to calculate the distances between sequences of genes and stuff like this. And after you do this embedding, PCA eigenvalues are always positive. We all know that. MDS eigenvalues need not always be positive. They can also be some negative eigenvalues. So you're embedding into Minkowski spaces with imaginary coordinates. And bioinformatics people typically like to throw away such imaginary coordinates. We believe that there is meaning to them, and so I'll show you what exactly is this meaning. But here is the setup. We take many, many networks, train them, calculate all these big vectors, project them down into lower dimensional spaces, and then we'll see what they do. Okay? So here's a picture. Every point is one neural network here. Okay, there's 6 different architectures: fully connected networks, CNNs, transformers, small ResNets, and large ResNets. They all begin training at essentially the same point up to statistical fluctuations called ignorance. P0 is that point. They all end at the truth. You don't see the truth in this plot. It is off the edge for reasons I'll tell you later. And what I've done is I took about these 6 architectures, trained with SGD, with nested acceleration, with Adam, different batch sizes, different learning rates, with weight decay, without weight decay, with augmentation, without augmentation, about 2,300 different configurations of networks, about 150,000 different points that are checkpointed along the trajectories of these 2,300 configurations. okay? When you plot the first 3 dimensions of this embedding, what you notice is that this is CIFAR 10, so the space in which these points live, these probability distributions live, is 50,000 samples times 10 outputs, so 500,000 dimensions, okay? In this 500,000 dimensions, the top 3 dimensions capture about 76% of the variance. This is telling you that in spite of the huge diversity in what these networks are, they live in what is basically a 3-4 dimensional manifold. I can write you down a description of each of these points in 3-4 coordinates, and it would be a faithful description. I wouldn't be cheating in the sense that pairwise distances would be preserved up to this much, okay? So this is the intrinsically low dimensionality of the optimization problem we are solving. The networks themselves have huge numbers of weights. A large ResNet in this case has about 40 million weights, and many others have comparable ones. In spite of that, it is a 3-4 dimensional problem, okay? So a large model and a small model, they don't learn different things. They not only learn the same thing at the end when they fit the data, but they also learn it in the same way. We can calculate distances between trajectories in the original space, and we can show that the 2 networks, large ResNet and small ResNet, they travel along the same manifold. It's just the larger one is a bit faster. So when people say that large networks work well, all that they're really saying is that the small network, I did not train it well enough. If I had trained it, perhaps it would work as well. Distillation, pruning are all evidence of such a statement, right? All these networks have the same manifold. That is also quite surprising. So not only is it 3-dimensional, but they also train in the same way. And they're all rather inefficient. So we can also calculate the geodesic in this space because this space is a product of spheres. And that would be, in some sense, the shortest path to take between the ignorance and truth. These networks don't take that path. They all take a slightly different path and somehow the same one, okay? These points that you see outside the manifold, we know who to blame for these points. It is Adam. Typically, when you train networks with Adam, you will see huge swings in the probabilities that are predicted for each of these images. But the cool thing here is that these points, if you were just to train them further, you would reach 0 error. So all the networks in this entire experiment have 0 training error, barring like a couple of dozen. So these points are aberrations of the training process, but they are not aberrant solutions. You just train them further, they will reach the correct solution. Okay? This is just the diffuseness of the manifold. So the training process explores a very low dimensional manifold in spite of this huge dimensionality. Yes?
So just to understand this, the lines that you have, they correspond to SGD?
The lines I have drawn by hand. They are just to guide your eye. There are different algorithms. So each of the colored points is one architecture, and within that there are 3 training methods, different variations of hyperparameters, different weight initializations, and so you can draw trajectory. You can connect the points of the trajectory if you want to look at it that way. Cool. So now let us project the same manifold in the top 2 dimensions. So this is PC1 and PC2. And what I want you to think about is that the second eigenvalue in this particular experiment of multidimensional scaling is negative. So this is a Minkowski space where this is a complex coordinate and this is a real valued coordinate. So distances in this space, they go as delta x square minus delta y square because y is imaginary, okay? P star is the point where everyone is headed. You can imagine that there is a light cone that comes out of P star. It is a light cone, the sides of which are points that have 0 distances between them. That is what it means for delta x squared minus delta y squared to be 0 if the eigenvalues were all equal. So these blue points in this case are all networks with 0 error. We know that the error 0 is reached long before the loss becomes small. And so all these different networks, they try to fall on the same light cone, of course, because that is the one of P star. And they have essentially 0 distances to P star, but tiny, tiny different distances. So the crossover loss is never 0, but it's very, very small and a tiny bit different from each of these networks. And the visualization method is plucking out these tiny differences. And this is very spooky. So you have 500,000 dimensions, And these probabilities are different in tiny, tiny ways. So you take one image and one network predicts 0.7 and 0.1, the other one predicts 0.65 and 0.12. The visualization method is showing you the difference. I'm plucking out signal from these large spaces somehow. And this is, I think, very mysterious why it happens like this. We have some hunches based on the analysis of the Ising model. We can talk about it later. But it's a way to understand the geometry, yes, in these high dimensions, but also understand anomalies in these high dimensions. OK, this is how the test manifold looks like. The manifold has basically the same shape, but then there is larger differences in trajectories of different architectures. Okay? In this case, you can actually see the truth. In the previous plot, you couldn't see the truth on the same 3D plot. Here, this is the truth. And if you think a little bit about what is happening, all these networks, they should be close to the test truth, right? Fully connected networks have 40% error, so they should be far away from the test truth. And then Korn mixers or large resonates have smaller errors, so it should be a little closer to the test truth. So you can think of the truth as the bullseye that you're trying to hit. And bad models are far away from the bullseye. Good models are close to the bullseye. And you would imagine that there's a big circle in which the bad models are spread around because they cannot get any closer. That's not really the case. The fully connected networks are all together. So they are all making the same mistakes. They are just bad, all of them. The Korn mixers are all getting the same things correct. They're all good in the same way. So this very classical bias variance trade-off that we imagine, the bias being this isotropic thing, is not really true. This is very clear evidence of this. The manifold here is a tiny bit higher dimensional. In this case, it is about 63% in the top 3 dimensions. But the structure is basically the same. We know that these branches come from, let's say, augmentation versus without augmentation. But there is very little differences. Okay. The same thing happens on ImageNet. We did not train as many models in this case, only 3 architectures. But the manifold is, again, low dimensional. And basically, all conclusions that we talked about are consistent. OK, so in this space, so the way we usually work, we've been doing this for a good year and a half now. We draw these pictures. We form hypotheses. And then do all the analysis in the original high-dimensional space so that we don't get fooled by the pictures, because interpreting Minkowski spaces is very hard. We have spent lots of months trying to do it. Yeah.
So from this lower dimensional picture, it seems like the transformer is doing worse than
no. So in this case, there is no negative eigenvalue. So Euclidean distance between the truth and the transformer, the end point of the VIT trajectory is actually how far the test error would be in this case. So I think if you're looking at the test error, these are 3D plots put on 2D paper. It's not that easy to say where this point is. I don't remember. OK, so what we have developed is ways to analyze trajectories in these spaces. And it's a little bit technical because different networks train at very different speeds. So we have to define some unique notion of time for all these networks. And the way we do that is we project all the trajectories on the geodesic, and then we imagine a constant velocity particle that travels along the geodesic and assign the time of the constant velocity particle to each of the networks. So a ResNet might make much faster progress towards the truth after 50 epochs than a small fully connected network. And then the ResNet will have a larger value of progress after 50 epochs. Okay? And so we can draw these dendrograms. I don't expect you to read this. But what I want to show you is these are dendrograms of trajectories of different configurations. I just focused on this one. These are all fully connected networks trained with different optimization algorithms. And you notice that when I clustered my dendrogram like this, all the architectures lit up together. So architectures is the predominant thing that distinguishes trajectories in these spaces. Within each cloud of architectures, the optimization algorithms cluster themselves into separate clusters. Okay? But basically, different architectures is what determines the differences in the learned models. Training hyperparameters of training or hyperparameters regularization basically do not matter. Yeah?
I would imagine the distance from the geodesic will kind of
So
contribute to. So you say your definition of time here depends on, like, you project the trajectory of the model on the geodesic.
Yeah, by just the great circle distance.
So the distance from the geodesic, of course, will contribute to. So what I
The
want to say
distance
is,
from the geodesic doesn't contribute to the time. But if the geodesic is, imagine the geodesic is a straight line, it is a straight line, and then the trajectories can go in different directions. So if you're kind of moving orthogonally to the geodesic, then you will not make progress. That is, yeah.
I guess, yeah, before you showed us that depending on the architecture, the trajectory, like essentially the trajectories depend on the architecture.
Mm-hmm.
So this is kind of another manifestation of that fact, or there's more information?
No, this is exactly the same data. I'm not showing you new data. I just analyze the trajectories a bit differently.
Yeah, I'm saying, so the way trajectories differ from the geodesic, you showed us earlier, depends strongly on the architecture.
No, right? So all the trajectories are quite similar to each other, and they're all different from the geodesic. There are differences in how similar. So for instance, all CNNs are a bit closer to the geodesic, and we don't know why, really. But in this plot, we treat the geodesic as just one other trajectory, and then this little black line that you don't really see very well is actually the geodesic. It is far from everyone. A better way to see this is this picture, where I did MDS for the probability models before. Now I'm doing MDS for trajectories. We have ways to calculate distances between trajectories, right? So we can again create a pairwise distance matrix, do MDS for that pairwise distance matrix, and every point now is one trajectory. And you see that the geodesic is far away from everyone. But the cool thing again is that all the architectures are close by. Okay? And in this case, for instance, this would be augmentation, or this would be no augmentation, so that it gets different clusters. Cool. Here is a slightly different experiment of the same kind. The red line here are models trained on the full ImageNet. Okay? And the green line, for instance, is a model trained only on all the categories in the vertebrate phylum. This is a subset of ImageNet, and you can just train a different model. We do some tricks of like how to plot in the same space these models trained on different tasks, as we can talk about it later. But the surprising thing here is that trajectories of models trained on different subsets of ImageNet still lie in a 3-4 dimensional space. So in the top 3 dimensions, the explained stress in this case is about 88%. So this tells you that not only is the manifold of networks trained on the same task low dimensional, the different tasks themselves, the endpoints of these trajectories are proxies for what the task is, the tasks themselves are low dimensional. The reason we are good at doing fine-tuning or transfer learning or multitask learning or meta-learning is because we are solving this 3-4 dimensional problem secretly. Okay? We can also do this very cute trick where this is the ontology of the classes in WordNet. These are the categories of ImageNet. You can take the distances between trajectories obtained from this analysis and then reconstruct the ontology. The visual classification task has a priori nothing to do with the ontology that was created from language, but they seem to be consistent with each other. And this is very cool because it tells you that there is some shared structure among tasks that goes beyond the modality and beyond this very abstract concept of this product manifold of probabilities. Okay. You can also do, in this paper, in the ICML paper, we showed a lot of things related to this. For instance, meta-learning or episodic meta-learning and supervised learning learn the same thing. Episodic meta-learning is just horrendously inefficient in how it gets to the truth. So there is no need to do meta-learning. You can just happily do supervised learning, and this is indeed what many people have started doing since we started saying it a few years ago. We also showed that self-supervised learning and supervised learning learn the same thing. Self-supervised learning doesn't go all the way to the truth. It stops midway because we don't really know where the truth is. We don't know the true labels, right? And you can do all kinds of analysis by this. The way I would summarize these pictures is that the manifold of probability distributions is looking like a hyperribbon, but the different tasks that we are interested in solving, they also project to the same parts of the hyperribbon. And this is why you do not need to change your model very much when you go from one task to the other task. All you need to do is modify the model in the sloppy dimensions. Those sloppy dimensions are the ones that are actually helping you transfer the model. And this you can make precise pretty easily. Okay. I won't worry about this result. I can tell you later, but let me conclude with. So, as I said, the success of deep learning is telling us new things about data. And we have really attributed terribly many mysterious properties to these networks over the years. It could be data that explains it. The second one is a tiny bit more philosophical. So it is very surprising why there is so much structure in the data. And if you think a little bit like a physicist, there is matter, there is molecules inside the table. They give the table certain properties like stress, strain, and why these properties arise is definitely a question of physics. What function we attribute to objects, the fact that images have objects, rooms have chairs, and chairs have some function, is of our doing. So the semantics that we attribute to data is really our choice. We don't go around counting the leaves on a tree. We don't go around giving labels to cats that depend on the number of hair they have, right? So we created these learning problems. They are easy because you want to identify this bunch of molecules in the next image as being the same cat. And it shouldn't be so surprising that we can learn the same structure in an artificial network. The problem was easy to begin with. Okay? So in a very vague sense, I would say that typical problems are learnable, and what is not learnable, you don't do. So I'll end there and take questions.
Thank you very much for a fascinating talk. And we already had questions from the audience, and we're running a little bit late. I don't know if there are questions online.
There are not, no.
OK. So maybe we have time for one very quick question. Yes.
So, so you constructed this low-dimensional embedding, and then use that as an argument that the tasks are easy because they're low-dimensionally embeddable. So I feel that there might be some element here that I'm missing. Couldn't it look different in a different embedding? Like could it be that a less successful embedding would give us not the same narrative? Just how does that work?
Yeah, so I think there is really two parts to that question. The argument that the tasks are somehow easy is, strictly speaking, a little bit of a speculation at this point. It doesn't follow from these results. So that's just right off the bat. The second part, which is this embedding gives us the low-dimensional structure. Would some other embedding not give it? Yes, you can create embeddings that wouldn't give you this low-dimensional structure. But it is a little bit of a question of analysis of sufficiency, right? There is structure in this high-dimensional space. This method plucks out the structure. If some other method doesn't, then that's the failure of the other method. So we are not married to Bhattacharya distance. So you're not married to the specific way of doing things. But it is true that there is this structure.
All right. Well, let's thank once again the speaker, and see you next Friday.